Welcome to the final video in the introductory level of applied maths for game development, and it's on basic trigonometry, part 13, unlucky for some. Alright, so trigonometry is it's the area of maths concerned with trigonometry. So trigon is just a fancy word for triangle, nothing to do with Teen Titans. But it's also inextricably linked to other geometric objects, especially a type of circle called the unit circle, which you've seen already. It's a circle which is exactly 1 unit in radius. And angles are also very important to trigonometry. For example, after all, every triangle has 3 angles in it. It's called a triangle, after all. Trigonometry needs to know a lot about degrees and radians. So you're probably used to seeing angles measured in degrees, where there's 360 degrees in a complete turn. This 360-degree system a lot of people think it dates back to the Sumerians or Babylonians, who used to track the sun's movement over a year, and they thought a year was 360 days. It also just happens to be a number that's quite easily divided by a lot of things, like by 60, for instance. But there are other ways you can measure an angle. You can measure it in turns, like a quarter turn, quadrants, which is like 90 degrees each. You can use something called arc minutes and arc seconds, which is really tiny degrees of measurement, 1/60th of a degree for an arc minute and 1/60th of that for an arc second. For very small geographical or astronomical stuff, we won't go that deep. There is something called gradients or gon, which is very close to degrees. It's 400 gons or gradients for a circle instead of 360, and they use that in surveying and in very few other places. But the one that's most useful to us is called radians. I think I have mentioned radians in passing once or twice already. So a radian is the angle of a circle subtended by an arc equal to its radius. If that sounds like gobbledygook to you, let me explain. But before I do, one radius is roughly 57.3 degrees, and 3.141, or pi in other words, radians, is exactly 180 degrees. And why is that? Well, take a circle, chop it into slices of pi, where the edge of the pi, the arc, is exactly 1 unit of length, and the radius is exactly 1 unit of length. Then what you'll get is a slice of pi where the angle in the middle is exactly 1 radian. Take another slice the same size, so the arc is exactly 1 unit in length, 1 radian. Another slice, 1 radian, which leaves a tiny slice left over, and add them all up, and you get 3.14159 rads, roughly, to be general, or pi to be exact. Look at it another way. Over here, if you start, and by the way, angles do typically start from this frame of reference, with 0 degrees being to the right along the x-axis. So if you start at 0 degrees and wind your way around the circle, you get to 1/4 of pi, 1/2 of pi, 3/4 of pi, and a full circle is pi. And you can continue that, so 5/4 of pi is down here, 6/4, 7/4, 8/4, but usually this area here is, instead it goes the other way, it goes minus 1/4 of pi, minus 1/2 pi, minus 3/4 pi. So at this point over here, positive pi and negative pi radians meet. So you can either say that an angle can be between 0 and 180, 0 and minus 180, or you can say the angle goes from 0 to all the way around to 360. Similarly, you can say the same thing with radians. You can say it goes from 0 to pi, or 0 to minus pi, or you can say that it goes from 0 to 2 pi all the way around. So that's radians in a nutshell. And any of those lines from the centre to the edge of a circle can be treated like a right angle triangle, like this line here, this hypotenuse it's pointing at. So that line becomes the hypotenuse of a new triangle, which has the adjacent and opposite angles over here. So we start along the line that's pointing out on the x-axis. You go a certain angle around from there, and you get this radius here, which is the hypotenuse of another triangle. Hypotenuse, by the way, is from the Greek phrase meaning stretched under, because they saw it as a bow, and the hypotenuse was stretched under the bowstring. Sorry, it was the bowstring stretched under the bow. So that's why it's called that. Now the trig functions are all over the place, but the 3 most important ones by far are sine, cosine, and tangent. And they're usually explained using the mnemonic SOHCAHTOA. Always reminds me of Skyrim. It's not Fusroda, it's SOHCAHTOA. And that is short for sine, or SOH there, is sine equals opposite over hypotenuse, SOH. And then CAH, which is the K, cosine equals adjacent over hypotenuse. And then TOA, tangent, equals opposite over adjacent. What all that means is if you've got a right angled triangle, and you've got an adjacent, there's the angle there that you're looking at, then the adjacent edge is the one along the x-axis next to it. The opposite edge is the one along the y-axis, which is opposite it, and the hypotenuse is the line that goes at an angle. And if you divide O by H, you get sine. If you divide A by H, you get cosine. And if you divide O by A, you get tangent. SOH, CAH, TOA, SOHCAHTOA. So the first of those, the sine function. Well, sine is from a rather convoluted etymological meaning, but basically it comes from the word sinus, which is, I think, Latin, which coincidentally perhaps means gulf. And the sine of an angle, here's an angle, and the sine of that angle from SOHCAHTOA is SOH, opposite over hypotenuse. It can also be calculated a few mathematical ways using repeating fractions, for example, such as Taylor or Maclaurin series, which looks like that. If you take x, whatever the angle is itself, if you take that actual angle to start with and subtract x cubed over 3 factorial, add on x to the power 5 over 5 factorial, then subtract x to the power 7 over 7 factorial, and so on until you get an answer that is accurate enough for you. That's an expanding fraction, which you can use to calculate sine without knowing the size of the opposite edge or the hypotenuse, which quite often we don't in programming. Typically we know x and y, and that's the opposite and adjacent edges, and we want to know what the hypotenuse is. Or we want to know what the angle is, or we don't always have all the details. Okay, so it can also be done using something called a chordic algorithm, which is fairly complex, but uses a complex number system as well. I'll leave that for now. The cosine function, by a similar idea, cosine, by the way, just means it complements sine, cosine, and the cosine of that angle there is adjacent over hypotenuse. And if you want to use Taylor series for it, it looks like this. The cosine of x, start with 1, subtract x squared over 2 factorial, add on x to the power 4 over 4 factorial, minus x to the power 6 over 6 factorial, and so on. If you're paying attention, you'll see that's a very similar function, different powers, but other than that, it's almost identical. Tangent, on the other hand, by the way, tangent comes from the Latin tangere or tangere, I'm not sure how you pronounce it. It means touching, because a tangent just touches a circle. And tan is the TOA part, so tan of that angle is equal to opposite over adjacent. So your y value over your x value. And those are the two variables that you most often actually know in this system if you're doing programming, especially games programming. So this is maybe the most useful one. The Taylor series for that, it's a bit complex. You start with x, so if you want a tangent of x, you start with x, add on x cubed over 3, add on 2 to the power x, 2x to the power 5 over 15, add on 17x to the power 7 over 315, etc. That one doesn't follow as obvious a pattern. Those numbers that you're dividing by are Bernoulli numbers, so they have to be calculated in advance. It's definitely the hardest one to work out by hand, but it can be done. So the sine function gives you a wave that looks like this. If you get the sine of every possible angle in radians and plot it as a graph, this is called a sine wave. Very common waveform. It starts at 0 because if your angle is 0, then that means you're pointing directly to the right. And therefore, if you do SOHCAHTOA, you look at that, the opposite edge, which is the y up the way, well, if you're pointed directly to the right, there is no up the way, so the opposite edge would be 0. So sine starts at 0 because of that. But as the angle increases, your circle just starts to point, instead of pointing straight across the right, it starts to go round and up. Well, the sine value also goes up at the same rate. And when your circle starts to go round and back down again, sine also goes down until it reaches 0. Eventually your circle will end up going back around on the negative, and that's what happens. The sine goes negative and comes back up again. So as it goes round and round your circle, the sine goes up and down and up because it's representing the y value. And in a circle, the y value goes up, down, back up again. So does the sine. Cosine, because it's working out the x essentially, you get the cosine of every angle and plot it as a graph, you get the cosine wave. And it starts at 1 because if you've got an angle of 0, you're pointing directly to the right, then your adjacent hypotenuse are equal. So from SOHCAHTOA, A divided by H will give you 1, they're equal, so it gives you 1. It's a little bit harder to visualize, but I did that next. So it starts at 1. You can see it's basically the same curve, but offset, so that it starts at 1. And that essentially recognizes, represents your your x value. So in your circle, we're pointing directly to the right, the x value would be 1. And as you go around the circle, the x value goes from 1 to 0 to minus 1, and then back to 0 and back to 1. Well, so does cosine, 1 to 0 to minus 1, and then back to 0 to 1. A little bit harder to follow why it's doing that, but that is what it's doing. It's tracking the x coordinate as the point goes around the circle, whereas the sine tracks the y coordinate. In a unit circle, of course, I'm talking about. So as the angle increases, the adjacent line gets shorter at first, passes the top of the circle and goes negative, and at the right-hand edge it starts to go back again. Now the tangent function isn't wave-shaped, but it's a sort of like an S shape almost, and it repeats. So at angle 0, when our circle is, we're pointing at the right-hand side of the circle, the opposite edge is 0, so 0 divided by anything for TOA, O over A, that's going to be 0. So tangent starts at 0 as well. And as we traverse the circle up the way, the x value gets smaller and the y value gets bigger. So it accelerates upwards very quickly. Well, not too quickly at first, but it gets quicker and quicker, basically. And at a certain point in our circle, we're going around the circle, eventually it's going to reach the x-axis. And at that point, if you try and divide, for tangent, if you try and divide x by y, y by x, and x is 0, so you can't really divide by 0. If you could, you would get an infinite number, and that's not possible, but it approaches infinity. And then there's a disjoint area where it's kind of approaching infinity that way, and then suddenly we cross over the y-axis, and you're dividing by a tiny negative number, and it jumps to negative infinity. So it kind of, the graph disjoints and jumps way to the negative, and then comes back again. Goes way up to positive infinity, immediately jumps to negative infinity, and comes back again. So that's why it's got that repeating pattern as it touches the y-axis. And then round again, it touches the y-axis and back to 1. Tricky one, that one. But as the angle goes, so does the opposite. When the angle reaches 90 degrees, the adjacent is 0, so tangent is infinite. When it crosses over, it's still a big number, but suddenly negative, and then the cycle repeats. This all links back to the unit circle. So imagine you had triangles that were parts of the unit circle. In other words, the unit circle R is 1, radius is 1 unit. You can easily do this just by scaling down any circle, and then anytime h appears in that formula, SOHCAHTOA, h is the radius, and it would be r. R equals ah equals 1. So in that case, SOHCAHTOA, SOHCAH, h is 1, and of course if you divide by 1, you're just left with the number you started with. So the sine of an angle is the y value of a unit vector, and the cosine of an angle is the x value. It doesn't really change tangent, but it means if you've got a unit circle, your sine and cosine are basically your y and your x values. So you can then scale back up again to your original radius. Remember, we scaled down our circle. So after scaling down and doing the sine and cosine, you can scale back up again. So that's why you see these formulas. We looked at them in a previous video. That's why these formulas work, because sine and cosine of an angle in a unit circle will give you x and y in a unit circle, but it's not a unit circle. So we then scale it back up by the radius of whatever size the circle actually is. So that's why we get r cosine theta and r sine theta to give us our x and y values. So if you know the polar coordinates, the angle and the radius, you can figure out the Cartesian coordinates x and y. And this diagram tries to illustrate that. If we know theta, 0.64 radians, for example, and we know r, 5 units long, then we can do cosine of theta, which is 0.8, and the radius is 5, so 5 times 0.8 gives us 4. So we can, from those two values, we can work out that x equals 4. And similarly, our sine theta. So sine theta is 0.6, r is 5, 5 times 0.6 is 3, so we get a y value of 3. So if you've got 0.64 radian angle and a distance of 5, that is equivalent to x of 4 and a y of 3, which takes us to this point up here. So r cos t, r sin t is a way of working out position based on an angle and a distance. So in games, you pick an angle to fire something at, like Angry Birds. That's the angle your bird is firing at, and r is the speed it's moving at. And r cos t and r sin t will tell you the x and y coordinates to move it in, the object in, because of course games work on a frame-by-frame basis in pixels. Okay, so that leads us to the inverse trig function. So remember, an inverse is when you have two operations that cancel each other out and bring you back to the number you started with. So the inverse of sine, we call it the arcsine function. The inverse of cosine is arc cosine, and the inverse of tangent is the arctangent. So for short, they can be called arcsine, arccos, and arctan, or for even shorter, you can say a sine, a cos, and a tan. Finally, they can also be called sine to the minus 1, cos to the minus 1, or tan to the minus 1. I don't like them, and you'll see why in a minute. But the reason why you can call them that is because of this logic here. If you've got a function a and an inverse function, a to the minus 1, imagine those functions aren't actually functions. Imagine they're actually numbers. So a and then a to the minus 1. Well, that's a to the minus 1 is just 1 over a. So if you multiply by a and then multiply by 1 over a, they cancel out their inverses, so you get back to the one you started with. So that's why we're seeing minus 1, sorry, to the power of minus 1 as being an inverse. But it's not actually 1 over a, or 1 over sine x. So sine to the minus 1x is not 1 over sine x, so don't fall into that trap. Especially annoying because if you saw sine squared x, that is shorthand for sine x all squared, which is not the case for sine to the minus 1, so it's a bit of one of those inconsistent things in math, and that's why it annoys me, but that's where it comes from. Don't get it messed up. Don't blame me, I didn't do it. If that's confusing, here's a simpler example. Let's take a function called f of x. Let's define f of x as, it's basically the successor function, but f of x equals x plus 1. So the inverse of that, obviously, which would be f to the minus 1 of x, that's x minus 1. So that's our function, that's our inverse function. Now, if you make y, this new variable y, equal to f of x, so that's the output of your function, y equals x plus 1. So that's the output of f of x. So if y is x plus 1, that's the output of f of x. And then if you put that output into the inverse function, f to the minus 1 of x, so f to the minus 1 of y gives us y minus 1, because it's just that formula there with y substitutes for x. So if you put in the output of one function into the inverse function, what do you get? Well, in this case, f to the minus 1 of y is y minus 1, but y is x plus 1. So x plus 1 minus 1, you get back to the number you started with, which is x. So if you put in the output to the inverse, you get back the number you started with. That's a bit of a hassle, especially for such a simple function, but the main point is, if you take the output of one function, f of x, and pap it into the inverse function, you'll always get back the original x. So essentially we swap what's on the right hand side and the left hand side to get back to where we started. The inverse trig functions follow the same idea. So if sine of theta is opposite over hypotenuse, then inverse sine of opposite over hypotenuse will give us theta, because of that rule we just seen about inverse functions. Similarly, cosine of theta is the adjacent over hypotenuse. So arc cosine of adjacent over hypotenuse would be equal to theta. We don't tend to use these much, especially in games programming, but this one is important. The tangent of theta is opposite over adjacent. And remember, that's y over x. So therefore, the inverse tangent, the arc tangent or tan minus 1 or whatever you want to call it, that inverse function of opposite over adjacent or y over x gives us theta. So this is the most relevant to one as just now. So if you do tan of theta, you get y over x, assuming a unit vector. The inverse tangent of y over x is theta. We just saw that. Or in programming, we tend to call it a tan because, well, mainly because a superscript of -1 is actually kind of hard to put into a text editor. So we call it a tan of y over x, gives us theta. So now you can calculate y divided by x and then run that a tan function either by writing your own Taylor series or using whatever library functions built in. So you can figure out what the angle is if you have y and x. I think I may have actually shown you that formula before, but that's the derivation. That's why that formula works. But here's the problem. What if your vector points straight up or down? If you're pointing straight up or down, then the x of that vector, so if you're pointing straight to the top, then 0, 1, for instance, x is 0. If x is 0, you can't do y over x, so you can't run your a tan function. Also, sometimes things go negative or positive when they shouldn't. Look at this. This is a lot to take in. Bear with me though. If your angle is 0, fine. There's an angle up to 90 degrees or pi over 2 radians. And at that point, x and y are both pointing to the right and upwards. So that's a positive number. They're both positive. So y divided by x, that's a positive number divided by a positive number. You'll get a positive answer. On the left-hand side, though, you get x pointing negative, whereas y is positive. And you divide a positive by a negative, you'll get a negative. You'll see why that's wrong in a minute. Bear with me a minute. So on the other hand, if you go the other way, x in this quadrant is still positive, but y is negative. You should end up with a negative answer. When you get to this quadrant, both x and y are both negative. Divide a negative by a negative, you'll get a positive. So a tan should give us positive, negative, negative, positive in these different quadrants. Sorry, I beg your pardon, it will give us those values, but it shouldn't for some of them. So in this area here, the angle should be 0, half pi, pi. So they should all be positive, but in this quadrant it's actually negative. So that's why that one's wrong. Excuse me. Whereas if the y value is pointing down the way, you should get a negative result of the a tan function. So it should go from 0 to minus pi over 2 to minus pi. These should all be negative, but these are negative, but these are positive. So the angles in here that it gives you will be wrong. So there's two problems. And here's the solution. We need to craft a method that handles these edge cases for us. It usually already exists. It's called a tan 2. But if you had to do it yourself, here's how you would do it. First, check if the x angle is greater than, sorry, the x value in your vector is greater than 0. If it is, let me take a step back. If it is, then that means it's in one of these two quadrants because x is greater than 0. So it's on one of these two quadrants where it actually gives us the right answer. So if x is greater than 0, just use a tan and it'll work. A tan of y over x. But if x is exactly 0, then it's either pointing straight up or down or something's wrong. If x is 0 and y is greater than 0, that means it's pointing straight up. 0, 1, for instance, pointing up the way. Then our angle we know should, when we can't calculate it using a tan because you can't divide by x, but we can tell it the exact angle because it's pointing exactly upwards. The angle is exactly pi over 2. Similarly, if y is less than 0, then we know it's pointing straight down and the angle is negative 90 degrees or negative pi over 2 radians. But if x and y are both 0, then you don't really have an angle. A 0, 0 vector doesn't point any direction, so we just say not a number. There's no answer. Now this else here deals with if x is not greater than or equal to 0. So therefore this else is when it's less than 0 and it's pointing to the left. So if your angle is pointing to the left and the the y value is greater than 0, it's pointing upwards. So this is to the left and upwards. Upper left quadrant. The upper left quadrant is when you get a negative output, but it should be positive from a tan. So all we do is we add on pi to flip it to the other upside down, so it's pointing up the way instead of down the way. Similarly, if the y value is less than 0, then it should be negative, but it's positive. So we just subtract pi to get it negative while still pointing in the right direction. So that is the solution, how to make a tan actually work properly for different quadrants. But it's so common we have it built in. It's called a tan 2. Now, I should look next at trigonometric identities, or trig identities for short. I won't bore you with evidence for all of these, but trig identities are important sometimes. There's loads of them. You can look up the rest of them online. I'm not going to go into all of them. In fact, even a few of these I'm just going to skim over. But the basic ones, the SOHCAHTOA, sine equals opposite over hypotenuse, cos equals adjacent over hypotenuse, tangent equals opposite over adjacent. Or you can put in the x and y and r values instead of opposite, adjacent, hypotenuse. So sine theta is x over r, cos theta is y over r, tan theta is y over x. But there's another identity I'm going to throw in here, which is that the tangent of an angle is equal to the sine of an angle over the cosine of the angle. An arc sine, arc cosine, arc tangent, they're all defined similarly. A sine of x over r is theta. A cos of y over r equals theta. A tan of y over x equals theta. We've seen that one at length, but they are basically the same idea. There are three more, which are seen occasionally: the secant, the cosecant, and the cotangent. And they're defined similarly to SOHCAHTOA. So the secant of an angle is r over x, the cosecant of an angle is r over y, and the cotangent of an angle is 1 over the tangent, the inverse of the tangent, which is also cosine over sine, or x over y in other words. And there's tons more that are even more detailed than that and don't even necessarily all have their own name. I'm not going to go into them just now. If you ever need them, just look them up. Now, the coding phase. In case you're curious, you can calculate sine using a repeating fraction or Taylor series. Here's how you would do it. I've set it to 10 iterations. That should be enough for a decent amount of accuracy. In fact, I'm not even sure you need more than that for a floating point number. You need more than that for a double, I would think. So if S is your angle, or is going to be our angle, we're doing 10 iterations, then their I value is going to go from 3 to, well, it's going to start at 3, because the Taylor series for it started with x to the power 3, I believe. And it went up by 2 each time. So you'd add on 2 each time until I reaches iterations doubled, 20 plus 3, 23. Why is that? Well, it's because you start at 3 and we go up 2 each time. So that is going to keep it doing 10 iterations. So 10 times it's going to take the sine, and that's going to work out whether the sine should be 1 or minus 1. That's a ternary function. It's basically like doing an if statement in one line. So if I divided by 4 gives you a remainder 1, then we have a positive sign, otherwise we have a negative sign. So that's going to flip back and forwards. Sign is going to be 1 for one iteration, negative 1 for the next, and so on. And then your angle, the actual angle we're working out, is that sign, so it's positive or negative, times angle to the power of I. So angle to the power 3, to the power 5, to the power 7, etc. as you go up, and divide that by the factorial of I. 3 factorial, 5 factorial. If you look back at the function, you'll see that is basically how it's made up. So that's how you can calculate sine manually. As you can see, it's not the most computationally cheap thing to execute. So try and avoid lots of sines if you're doing them every frame. Cosine, it's a similar thing. So you start at the angle being squared, and then it goes up to power 4, then to power 6, power 8, etc. 10 iterations, either multiply by 1 or minus 1, It's basically the same idea, but with just a different powers that you're going to work on. And that'll give us the cosine using a repeating fraction. Tangent can be done using a repeating fraction, but it's really tedious because of those Bernoulli numbers. We could write it all out if you really wanted, but it would take more than a couple of slides. So I'm going to check it out and use an identity, which we're going to run sine and divide it by the cosine. So that looks like it's going to be twice as computationally expensive, but actually I'm not sure it's quite that bad, because if you were doing it the other way, you'd have to work out the Bernoulli numbers. So I'm not sure that's actually all that much worse than doing it the proper way. Chordics, of course, are even better, more efficient, but they're even more hard to understand, so definitely not for now. This is the atan function. If you really wanted to do it yourself, then it's oh sorry, I was worried about taking a step back. I thought I was still talking about tan. Sorry about that. This is the atan function, and it can be done using a repeating fraction as well, very similar, S angle at 500 iterations. And the difference for this is because the numbers can be so large with atan, it needs a lot more iterations to get the same level of accuracy. So this is definitely not an efficient way of doing it. There's definitely better ways using chordics, but this will work, and it's going to do lots of powers with huge powers and huge numbers and so on. So it's definitely not efficient, but it's basically the same idea. It's just to show you can use a similar thing for a tan, a sine, even a cos, but not today. And finally, the last thing we're going to do is show you an example of using trig functions to rotate an object. So we're going to have r and theta, that's our polar coordinates, the angle is theta, and the distance that we're going. So the distance is simply x squared plus y squared all root, which is Pythagoras theorem, square root of x squared plus y squared. Shouldn't be too much to get your head around there. And theta is using a tan 2 of y and x. You put it in that order because that's the order it does the division, by the way. So almost every a tan 2 function has it in that order, and it'll run all that code that I showed you earlier just to make sure that you've got the right quadrant and the right positive or negative value. But that's all done for you, it's baked in. So if you've got a vector with an x and y, you can run these two lines to get x and y turned into r and theta. Once you've got the r and theta values, you can then just change theta. So in between these lines, you could increase or decrease the theta angle to make it rotate. And then once you've done that, you then calculate the new vector, which would be r cos theta and r sin theta, because you've seen that they give us the x and y values. R hasn't changed. Theta may have changed. You may have changed the angle in between here. Whatever that angle is, the new angle, if you use r cos theta and r sin theta, you will get the x and y values of your new vector, your output vector. So that's one way you can rotate an object. It does use atan, cos, and sine, so it may not be the most computationally efficient, but I mean, computers are pretty fast, and as long as you're not doing this a lot, then you can probably get away with that. But I'm using it here just to illustrate that you can do this sort of thing using trigonometry instead of complex numbers or any other kind of stuff like that. But I think that will do for now.